What if the universe doesn't end in fire, but in silence? Not with a bang, but with a slow fade into darkness and stillness. This scenario is called the heat death of the universe, and it's one of the leading theories for how all stars, galaxies, and even matter itself may end. To understand heat death, we need to talk about entropy. Entropy is a measure of disorder, or more precisely, how spread out energy is. The second law of thermodynamics tells us entropy always increases. Energy naturally disperses, becoming less useful for doing work. The universe began in an extremely low entropy state with the Big Bang. That imbalance gave rise to stars, galaxies, and eventually, life. But over time, entropy keeps rising. Energy spreads thinner and thinner, until no useful energy remains. Project forward trillions upon trillions of years. Stars exhaust their fuel. White dwarfs and neutron stars cool into black, invisible remnants. Even black holes, the final anchors of structure, will slowly vanish by releasing Hawking radiation. It means black holes aren't eternal. They actually emit tiny amounts of energy and, over unimaginable timescales, evaporate. But that radiation is extremely diffuse. Each black hole essentially leaks its mass back into the universe as faint particles and photons. Could this energy ever clump together to form new stars or galaxies? Unfortunately, no Hawking radiation spreads evenly in every direction. It doesn't concentrate, and without gravity binding large amounts of matter together, it can't collapse into anything new. The universe at that point is so vast and so empty that the radiation simply dilutes into the cosmic background. Instead of fueling new creation, it just adds to the thin haze of energy that drives the cosmos further toward equilibrium. But what about the possibility of Hawking radiation emitting from several black holes and colliding? Could this generate enough energy to form new galaxies? The radiation emitted is at such a low density, and combine this with the expansion of space itself, the chance of any meaningful collisions is essentially zero. In addition, Hawking radiation is emitted as photons, neutrinos, and maybe even electrons and positrons, which means they would not gravitate and clump together, but would rather just scatter or annihilate into more radiation. So when we talk about heat death, we don't mean everything gets hot. Quite the opposite. It means energy is perfectly balanced everywhere, no temperature differences, no gradients. With no imbalance, nothing can happen. Think of a cup of coffee. While it's hot, energy flows into the cooler air. But once coffee and air reach the same temperature, nothing interesting happens. That's heat death, except scaled up to the entire universe. Current evidence suggests the universe's expansion is accelerating, thanks to dark energy. If that continues forever, heat death is the most likely destiny. The timescales are almost beyond imagination, so long that even the word trillions feels too small. But the concept itself is powerful. It reminds us that everything we value, life, creativity, complexity, exists because of temporary imbalances in energy. Without them, there's only equilibrium. The heat death of the universe paints a sobering picture, a cosmos that began in brilliant light, ending in endless night. Yet in the fleeting middle, right now, stars burn, galaxies swirl, and life has the chance to reflect on it all. Perhaps that's the real miracle, that in a universe destined for silence, we get to ask questions and tell its story.